Okay, so notes 10.10 is alternating series error bound. So the very first part of this notes, think of it like a proof. You're not going to have to actually solve or do a problem like this, okay? This is helping us make the connection between an alternating series and an error bound. And once we make that connection, you won't have to do this first part again. So looking at our example is an alternating harmonic series. So remember, a harmonic series does what? Diverges. But an alternating harmonic series does what? Converges. So in order to do an alternating series error bound, we have to make sure it converges. Okay? So if the series does not converge, then you cannot find the error bound. Okay, that's the most important. So in the example that they give us this series, the summation of n equals 1 to infinity of negative 1 to the power of n plus 1 over n. And what I'm supposed to do is give you time to fill in this table with your partner next to you, but for the sake of time, I'm just going to fill it in. So just keep in mind, remember that when we learned about a sub n, that is terms, meaning if you plug in all the values of n, you would get a sub n. And then remember, s sub n is the partial sum. So for example, if you're trying to find the partial sum of s sub 3, that would be you adding a sub 1 plus a sub 2 plus a sub 3. That would be the partial sum. Okay, so filling in this table, if you were to plug in 1 through 8 into the series for n, you would notice that the values are alternating from positive to negative and that the fractions are decreasing. Okay, so these are the values that you would get.
Colby, please put your phone away.
Okay, and then we would convert all of this into decimals. So 1 stays as 1, negative 1/2, 0.5, etc. So I'm just going to copy all these down. Okay, the decimals are there because it's going to help us graph this in just a moment. So it's not something that you would have to convert to decimals, but decimals are easier to graph than fractions. Okay, and then for the summation, again, if we're looking at the very first one, s sub 1 would just be 1 because it's all the values before. Okay, and there's no values before, so it's just 1. S sub 2 would be us adding the first two. So 1 plus negative 1/2 is positive 1/2, and then so on and so forth until you got to the end. So these are the values. Plus, if you were doing this by hand, it would probably take you a little while because you'd have to do lots of common denominators in order to add this together. And again, another reason why we convert it all to decimals. Okay, all these decimals have more decimals after it. I just rounded to 2 to 3 decimal points. Okay, and what it wants us to do next in order to see this alternating series is it wants us to plot the points n, comma, s sub n. So n is all the values that we plugged in, 1 through 8. S sub n are all those fractions or decimals that we got at the very bottom for the partial sums. Okay, so if I was to label my axes, I would label my y by 0.1 all the way until I get to 1. Okay, and again, this is going to be s sub n. We're going to treat that as our y value. In the bottom, I can just number by ones, all the way till 8. And this is n. Okay, so then from here, I'm going to plot the points. So again, I'm plotting it as n comma s sub n. So my very first n was 1, and if I go down to s sub n, it's also 1. So it's 1, 1. Okay, my next one, n is 2, s sub n is 1/2, and so I'm just going to keep doing that until I plot all my points. Okay, and so what it should be looking like is every point that you plot, you have a point above, a point below, above, below, and these points are slowly getting closer together. Well, if we were to actually look at the series above, that series is actually an approximation for the function natural log of 2. Okay, so the series above is an approximation for the natural log of 2. We're going to actually call that s. Okay. And if we were to plug that into the calculator, it would be 0.6931. So again, I found natural log of 2. I didn't randomly think of that number. I just know, because I have my information off to the side on my notes, that this series is an approximation for natural log of 2. When we're going through these problems, in the beginning, they're going to tell you what functions we're approximating. Okay, towards the end of this notes packet, you'll be able to do that on your own. Okay. And so since the actual sum s is 0.6931, I'm going to go ahead and I'm going to plot that line. Okay, so it's right below 0.7. And so now if I look at the points, I should notice that the points, as my n value increases, is slowly approaching that line, which means they're slowly approaching that actual value. Okay, which means the more n values we have, okay, the closer our approximation is to the actual value. And so to show that, on this table, we're going to go ahead and we're going to find what is called the error. And if you've taken statistics or in statistics, this error is actually the residual distance, okay, from the observed versus the exact point. Okay. And so that would be this here. So this distance. Notice that this distance is a lot larger than this distance. Okay, which means the error is going to be a lot larger here and a lot smaller here. Okay, we want our error to be as small as possible. That means we are using our approximation to get as close to our actual answer. Okay, so again, just showing this for you guys, you're going to have to write a little small here, is we're taking the actual value s, so that's the natural log of 2, and we're going to subtract each of the Sn values. So I have the absolute value of natural log of 2 minus 1. That gives me 0.31. Okay, the absolute value of natural log of 2 minus 1/2. So I'm going through each of the Sn values, and I'm just writing the Sn values as fractions to kind of save a little bit of space. I know it's going to be a tight fit in here. And then we just continue that all the way down. So I'm just going to continue writing this out. And if you were to actually solve this out, like the natural log of 2 minus these values, you're going to get a decimal that is much larger than the one I'm writing. I just rounded it to 2 decimal places. Okay, and to make it even easier if you wanted, as long as you show like the first couple with the actual natural log of 2, hopefully that's going to, help you remember to go back and see where these numbers are coming from, and then you should just write the decimals for the rest of them. Okay, so notice, again, looking at these errors, as we increase the end value, the errors are getting smaller. Okay, and that's what we wanted. So what we just did is we just proved alternating series. Okay, and how alternating series eventually is going to converge to the actual answer or the actual number. Okay. So now this next part is the part that is for calculus, right? What we really need to focus on, and it's how to use alternating series for an error bound. Okay. It says if you have an alternating series that converges, that's the most important, we can approximate the sum of the series. So the formula for this is going to be the absolute value of s minus s sub n, the error, is equal to the absolute value of r sub n, which is the remainder it's sometimes referred to, or we're just going to use the term error, is less than or equal to the absolute value of a sub n plus 1. Okay, so again, this is the error. This is the error bound. Okay, so for these notes, as long as we have that formula, the practice part, so the examples we're going to look at next, should be simple enough to solve. Any questions so far? Okay. Okay, so let's look at number 1. Number 1 says determine the number of terms required to approximate the sum of the series with an error less than 10 to the negative third power. Okay, so the first thing we're going to do is we're going to write down our equation. So the absolute value of s minus s sub n has to be less than the absolute value of a sub n plus 1, okay, which has to be less than our error. Okay, well, our error is given to us. It says error is less than 10 to the negative third power. So I'm going to write that there, 10 to the negative third power. Okay. So the next thing that I have to do is I have to find a sub n plus 1. So if I look at my series that they gave me, remember when looking at this alternating series, I want to take the absolute value of it, and that gets rid of the alternating series. So now instead of having negative 1 to the n power on the top, I only have what on the top? Just 1. So this is now 1 over n, and that is my a sub n. Okay. So in order to find a sub n plus 1, what is that going to be? One over, don't overthink it, n plus 1. Right? We just take n and add 1 to it. Okay, again, we know that this has to be less than 10 to the negative third power. Well, that's the same as writing 1 over 10 cubed. Okay, which is another way of writing what? 1 over 1,000. Okay, so once we get to this part, we just need to solve for n. And so in order to do that, we could do what? Cross multiply. Good, so I get, I forgot the 0 right here. 1,000 is less than n plus 1. Okay, I cross multiply, or butterfly method, however you learned it. Okay, and then the last thing I need to do is what? Subtract 1. So when I subtract 1, I get n is greater than, I'm just making sure n comes first, 999, and that is my answer. So the explanation, the proof of this is a lot more complicated than what we're actually doing. Yes.
So on the equation that we had before, did we flip the error and the error bound? Because it says the error bound is greater than or is greater than or less than the error. So is the error?
So the error is the s minus s sub n. So it's saying s minus s sub n is equal to r of n, which is less than or equal to a sub n plus 1.
Okay.
But since our problem said find an error that is less than 10 to negative 3, that's how I knew I was using the less than symbol.
Okay.
Okay, number 2 says if the following series is approximated by the partial sum with 10 terms, what is the alternating series bound error? So anytime you see this, alternating series error bound, this is the absolute value of a sub n plus 1. That's this. Okay, so if I look at my original series and I take the absolute value of the entire thing, that gets rid of the alternating series, and I'm only left with this, the 1 over 5n plus 2. So if I need to get a sub n plus 1, what am I going to add to the n? 1. So that means this is equal to 1 over 5 times n plus 1 plus 2. I just added 1 to n. And then it says the partial sum with 10 terms. So this 10 is representing what? N. So I'm just going to plug in 10. So this is 1 over 5 times 10 plus 1 plus 2. And that is equal to 1 over 57. That's my answer. But do you see how the previous notes were building up to this point? Like, we would not know to take the absolute value of the series to get rid of the alternating series if we did not do the previous notes. Okay, any questions on 2? Okay, number 3 is calculator active, which means you have access to Desmos. So it says approximate an interval of the sum of the series using the alternating series error bound for the first 5 terms. So anytime it wants you to approximate, you're going to find s sub n. And in this case, n, since it's talking about the first 5 terms, is going to be 5. So first we need to find the approximation, and that is s sub 5. Okay. In order to find that, we just look at our series, okay, which is already given to us, and we're going to do the summation of n equals 1 to 5. So instead of having it to infinity, we're stopping at 5. Okay, and then we're going to write that entire a sub n. So negative 1 to the power of n plus 1, 4 over n squared. And then you're going to plug this entire thing into the Desmos. Okay, and you're going to get an answer, and that's 3.354 repeating. Okay, the only thing I would keep in mind when typing this into Desmos is to make sure that your n plus 1 value, so this part on the exponents, for whatever reason, Desmos wants you to put that in parentheses or it won't calculate it for you. Okay, and I know it has to do with PEMDAS and the order of operations, but just put this part in parentheses, and then it should work. Okay, it's not going to give you a wrong answer, it's just going to pop up an error. Okay, and now that we have this value, we need to find the error bound. So remember, the error bound is always the absolute value of a sub n plus 1. Well, since our n value was 5, n plus 1 is going to be finding a sub. We already started at 5, so plus 1 would be 6. We want the next term. So we need to find a sub 6. Well, since this is an absolute value, we know we could go back to our series, put this series in an absolute value. That gets rid of the alternating series, and we are just left with 4 over n squared. Okay? Since we're finding a sub n plus 1, and we already said that value of n plus 1 is 6, I'm just going to plug in 6 for n. So this becomes 4 over 6 squared, which is 4 over 36. change that to a decimal. It's 0.111 repeating. Okay, so for these type of problems, you need the approximation and you need an error bound. And what it wants us to create is an interval. Okay, so since we already have both of these things, in order to create that interval, that would be us adding a value and subtracting the value. And that means S, the actual sum of the series, is going to be between those two values. Okay. So for example, if I add 3.354 to 0.111, I'm going to get 3.243 repeating is less than or equal to the actual sum S, which is less than or equal to, and then now I'm going to add those two values together. And so I get 3.465 repeating. So this answer of the interval is what they were asking for, so this is the answer. It is just like stats. Yeah, this is very similar to stats. Yes, question?
Wait, sorry, so you just added, subtracted for that side and then added on the other side?
Yes. I took these numbers and subtracted them. That's the lower bound. I took these numbers and added them, and that's the upper bound. So yeah, this section of notes has a lot of similarities to statistics. Okay, so last example, number 4. It says let f of x equal the following series. Show that 1 minus 1 over 3 factorial approximates f of 1 with an error less than 0.01. Very common multiple choice question. And it looks much harder than what it actually is. Okay, so the very first thing that you're going to do is you're going to write down that formula. So I have absolute value of s minus s sub n is less than or equal to the absolute value of a sub n plus 1. Okay. Now, reading this, it already gives us what s is. S is f of 1. Okay, remember s is the actual value, and it wants us to use this series to approximate that. So we already have s. Okay, s sub n is going to be that approximation. So this part that they gave us. So I'm just going to plug that in. So I have the absolute value of f of 1 minus 1 minus 1 over 3 factorial. And I need to see that this is less than or equal to a sub 3. Can anyone tell me where I'm getting sub 3 from? Let's see if this helps. Okay, remember the series is always going to give us the terms A1, A2, A3, etc. So notice when they gave us the approximation of 3 factorial and an x value of 1, okay, that came from a sub 2. But if I want a sub n plus 1, that means I need a sub 2 plus 1, which is a sub 3. Okay. I know that a sub 3, if I plug in 1 for x, is 1 over 5 factorial. Well, 1 over 5 factorial is 1 over 120. And if I was to convert 0.01 into a fraction that resembles the same thing, that fraction would be what? 1 over, what place is it in? The hundredths place, so 100. 1 over 100, and we just proved our answer. We just proved that this error is going to be less than 1/100ths or 0.01. Yes?
Wait, I'm sorry, I didn't understand that.
Which part?
Okay.
Where did I get the 1 over 100? Well, we're trying to prove this. We're trying to see if the error is less than 0.01. 0.01 is 1 over 100. Okay, I could have done this a different way. I could have converted this to a decimal, and maybe that would help you more. whatever 1 over 120 is as a decimal is still going to be less than 0.01 as a decimal. The only thing is you're not always going to have access to Desmos here, so you're not going to be able to convert this to a decimal. However, you should, hopefully, fingers crossed, know how to convert a decimal into a fraction.